एक पेशेंट है वो उसको बच्चा नहीं था।
Okay, so hello all. Till now it is not on YouTube. Actually, still aiming to create YouTube channel. Actually, it is in process. We are going to get a Gmail, then we'll create a YouTube channel. So still it is in process. And yeah, I don't know. Very few people have joined today. The second thing is the guest will join soon. Actually, it's in the way.
Sir, so shall we start or shall we wait for 2 to 3 minutes more?
Yeah, 2 to 3 minute rule. So if you want to say something, Nusra, you can say. Do you want to say something?
No, no, it's fine. It's fine. Then we'll start after 2 to 3 minutes.
Okay. So, yeah, hello all. So now uh, Mansu is with us, and he is going to discuss with whatever they have the topic fractals. Okay. So, Anushka, do you want to say something?
No, sir, it's fine. Then we can start off. It's 7:10, so we can start off the
Okay.
seminar.
Okay, fine.
So, hello all. I'm audible. I hope so.
Yes, yes, sir, you're audible.
Okay. Today in this talk, we are going to discuss the fractals. We are going to be very basic here. Before we proceed, let us see some fascinating fractals here. Here, this one is the broccoli. The second one is an example of a natural fractal organ, which is the lungs here. This one is called the lungs, the human lungs. Let's move to the third one. This one is called the couch snowflake. And this the fourth one is known as the Sierpiński carpet. Let's go ahead. This triangle shaped, this one is a canonical example of a fractal. This is known as the Sierpiński triangle. So observing these figures, are you able to see one of the common features shared by all of these fractals? Yes, one of you. any of the common features which you are able to identify, that feature is shared by all of these fractals. Yes, one of you. Any of the similarity you are able to see?
The
Yeah, please.
pattern is going infinitely.
Sorry? Pardon?
There is a pattern in each image that
In
is going infinitely.
what kind of pattern you are able to see? Any specific pattern? Obviously, there is pattern, but what pattern?
So the recursive pattern.
Sorry?
Recursive pattern.
Recursive, what does it mean here?
Self-repeating.
Exactly. Here, the common feature shared by all of these fractals is a self-similarity. That is, the smaller parts resemble the whole. If you pick a small piece of one of these pictures, it will resemble the entire picture. That is, it is a scaled version of the entire one. Such features are shared by the fractals, these geometric objects. So let's go ahead. However, in this talk, we are going to concentrate on one of these fractals called the Sierpiński triangle. Let's start. Let us start with an equilateral triangle. This is an equilateral triangle. Now, what we do here, we connect the three sides of this equilateral triangle. That is, we connect the midpoints of the three sides of this equilateral triangle. Now, what we do here, we remove this triangle. Just remove this. Let me iterate once again. We start with a filled equilateral triangle. We connect the midpoints of the three sides of this equilateral triangle. We remove the triangle at the center. This triangle is removed here. Remember that this triangle is a filled equilateral triangle. I mean the solid equilateral triangle. Now we are removing the triangle at the center. Remember here, we are removing the open triangle. Open triangle means that we are only removing the interior of this triangle. That is, the boundary of this smaller triangle remains there. Now, let's start once again. We have an equilateral triangle. At the second stage, we connect the midpoints of the sides of this equilateral triangle. We remove this one. We remove this open triangle, I mean the interior of this triangle. Now we repeat this procedure for each of these smaller triangles, for this one, for this one, for this one. I hope you all are getting this. That is, this triangle, the original triangle, this one, is divided into three smaller triangles. And these three smaller triangles are congruent. These three smaller triangles are filled as well. So let's see here once again. So if we repeat this process ad infinitum, that is, this process is repeated infinitely many times, we obtain the Sierpiński triangle, this one. And observe how does it evolve. See the left one. This is the way we evolve here. First, we take this triangle. We take this solid filled equilateral triangle, this one. Then we connect the midpoints and remove the triangle, this open triangle. We remove this one. And we repeat this process for the remaining smaller triangles. This is what we obtain here, and so on. So if we iterate this process infinitely many times, what we obtain is a Sierpiński triangle. Yeah. Are you able to see what is the perimeter of the Sierpiński triangle? Yes, one of you. Can you make some comments on the perimeter or the area of this triangle? I mean the Sierpiński triangle. Yes, one of you. Any comments? Yeah, please.
So the perimeter is the same as the original equilateral triangle, but the area seems to be going to 0.
The area tends to 0, but the perimeter tends to infinity. Are you able to observe this?
Why is the perimeter tending to infinity, sir?
Yeah, I'm coming to the fact. Again, how did we start? We started with an equilateral triangle, a solid filled equilateral triangle. At iteration number 1, let us see this one. What happens? we connect the midpoints of the three sides of this equilateral triangle, and we remove the triangle at the center. But remember here, we are only removing here the interior of this triangle. The boundaries remain there. We don't remove the boundary of this triangle, the triangle at the center. So at each iteration, the number of edges is getting increased since we are removing the open triangle. The boundaries remain the same, remain there. So here, these three edges are increased. At iteration number 2, we repeat this process for each of the remaining smaller triangles. Again here, we are removing this one, the interior of this triangle. The boundaries remain there. So again, the number of
Sorry, guys, there's some network issues. Sir will be joining soon. Sir, you are inaudible. Hello?
Okay.
Yeah.
Sorry.
Okay. So let me repeat this once again. We started with a solid filled equilateral triangle. We connected the midpoints of this equilateral triangle and formed a new triangle. So this original triangle is now divided into 4 smaller equilateral triangles. Now we remove the triangle at the center, but we remove only the interior of this triangle. The boundaries remain there. So this is the triangle we obtain. Now we do this process for each of the remaining smaller triangles. This is what we obtain, and we do this process for an infinitely many times. So what we obtain is the Sierpiński triangle. So here we are able to see here that the perimeter of this triangle tends to infinity. The reason is that at each iteration, the number of edges is getting increased. And what would be the area? The area tends to 0. So let us discuss this mathematically. How does it happen? Though it's very simple.
Sir,
Yeah,
what triangle is that? Can you write down?
your voice is not clear. Some noise is there. Can you repeat once again?
Sir, what triangle you're talking about? Can you write down?
What? I'm not getting. Can you write in the text? Can you write in the chat box?
Sir, you're naming this triangle, right? What triangle?
The name of the triangle is a Sierpiński triangle. I'm writing it down. Just a second. Yeah, you were asking the name, na?
Yeah.
This is called the Sierpiński triangle. Or Sierpiński gasket. This is called Sierpiński carpet. This is called cork snowflake. This is the evolution of this Sierpiński triangle. And the first one is very clear to everyone. This is the broccoli and this is the human lungs. Okay. Yes, anything else? Shall we go ahead? Okay. So let us see how is the area tends to 0. Area of the Sierpiński triangle it tends to 0. Let us see how does it happen. Let A naught be the area of the original triangle. then what would be the area at the first iteration? Again, let us see once again the evolution here. See this evolution. What happens? We connected the midpoints and we obtained the 4 smaller triangles and we removed the triangle at the center. So, yes, what would be the area even?
3/4 of the area of the
The original triangle A0 minus 1/4 of the original triangle. That gives 3/4 of A0. Is it correct?
Yeah.
And we repeat this process. So at the kth iteration, the area would be 3/4 raised to the power k times the area of the original triangle. Is it correct? Yes? Yes, one of you.
Yes, sir.
Okay. So as k approaches infinity, where does the area tend to? The area tends to 0 as k approaches infinity. Since the number 3/4 is less than 1, you can apply the ratio test or whatever. So mathematically, we are able to express that the area of the Sierpiński triangle tends to 0. Now let's go ahead. Let's see about the perimeter. As I told, that after each iteration, the number of edges is getting increased. Therefore, the perimeter must increase. So at the kth iteration, or I should write after the kth iteration, after the kth iteration, okay, after the kth iteration, what would be the perimeter? How many edges is getting increased? Yes, one of you. Observe. This is iteration I0. At iteration level 1, how many edges is getting increased?
3,
At this stage, iteration number 2,
9,
and so on. At the kth iteration,
3 to the power k.
okay. So after the kth iteration, the number of edges is getting increased is 3 raised to the power k. And the length of each edge is 1/2 raised to the power k. Is it correct? Is it correct?
Yeah, that's right, sir.
Okay. So the total length would be the sum of the products 3 raised to the power k multiplied by 1/2 raised to the power k. And for this Sierpiński triangle, this k should vary from 1 to infinity, or you can take from 0 to infinity. That would also be fine. That should mean the sum, this infinite series, 3/2 raised to the power k, k varies from 1 to infinity. Now, what would be the sum? Is this a convergent series or a divergent series?
Diverge.
So this series is a divergent series. This series diverges. So what we conclude, we are able to see a figure, a geometrical object, which is a Sierpiński triangle, whose area is 0, but the perimeter is infinite. So what happens in the Euclidean geometry, we study with lines, points, circles, the very regular figures. But what happens when we have an irregular geometric object, which is very irregular, which is very rough? The Euclidean geometry is incapable of describing those objects. So their fractal geometry surpasses this Euclidean geometry. And one of the objects we saw is the Sierpiński triangle. Okay, let's go ahead. Now let us see the Koch snowflake. What we do here, let us take again an equilateral triangle. Pick one of these line segments. Okay. Now what we do, divide it into 3 equal parts. Now forget about this one. Forget about this one. And add an outward bends here. So how does this look? This looks like this one. and repeat this process for each of the remaining sides. How does it look? Let us see the figure here. This is the Koch snowflake. I hope you are getting this figure, or should I draw it properly? Yes, one of you. I hope you are getting how does this figure look like and how we are able to.
Sir, will you please show it once again?
Okay. What we do, we take a straight line. Okay. Now forget about its middle part. We remove this part. Now what we do here, add an outward bends. Is it fine? Now we have this equilateral triangle. This straight line segment has been changed to this one. So this has been changed to this, like this. Now we do this, whatever we have done for this base, do the same for this straight line and this straight line. So how does it look? Yes, I'm getting some noise. Please. This looks like that. Now do this process for all these smaller lengths. Do the same process for this one, this one, this one, and so on. So what would get? We would get this Koch snowflake. Is it clear now? How do we obtain? How do we construct this one?
Yes, sir.
Okay. So now tell me, what would be the perimeter here? Yes, please mute yourself. Accident. Yeah. Yeah. What is the perimeter of one of you?
I think the perimeter should diverge in this case.
Yeah, exactly. The perimeter again is tends to infinity. The area.
Area is going to be finite actually.
Yeah, the area is finite, but the perimeter is infinity. Yes. What is the difference between the Sierpiński triangle and the Koch snowflake?
Was it?
Yes.
Well, in one case we removed some part. Right now in this case we're going to just flip that. I mean, some part is getting added up always kind of.
Okay, that's fine, but I need some response in terms of the area and parameter. The parameter in both the cases tends to infinity. What about the area?
Area is, I think, 8 by 5 times the original area, I believe.
I don't need a precise answer. Even I also don't remember. But visually, we are able to see here that the area in the case of Sierpiński triangle tends to 0. But here in this case, the area is a finite number.
Yeah.
Non-zero. So this is the basic difference we have. Okay. Yes, any comments, any queries till now? Yes. Yes, any comments, any queries?
Sir, is fractals all about geometry, or do they have any other like algebraic or other sort of use?
Fractal is actually multidimensional. It finds we can relate fractals to any of the branch of mathematics, whether it is algebra, whether it is analysis, whether it is geometry. And it finds applications everywhere, not even in mathematics, but also in allied fields like economics, engineering sector, everywhere. Yes, are you convinced? Yes.
Yes, sir.
Okay. So
Sir,
let us.
I joined late, sir. Where will this session is recorded?
Yes.
Recording?
Yeah. Yes.
Where will it be available?
It will be in the same group. Will be posted. Have you joined the Pi Square seminar group?
No.
Okay, so when the next next mail will notification will be shared, will be to all of you. Then in that I will try to paste the link of this, and after that I will actually creating the YouTube channel, but till now it is not created. Very soon it will be created because holidays now. I will be shared.
Okay, sir.
Yeah.
Okay. So now let us see a concept called fractal dimension. So we are going to discuss it in a very loosely manner. but okay, it's fine. Fractal dimension. In Euclidean geometry, we know the dimension of a line is 1, the dimension of a square is 2, and so on. But what happens about the dimension of the Sierpiński triangle? Can we answer this? The answer is no. Euclidean geometry is incapable of answering those questions. So here comes the fractal geometry, where we are going to discuss fractal dimension. Let's see here. So what happens? Let us take some terms. N is the number of small pieces of the fractal. S is a scaling factor. And it is represent D or the fractal dimension. So the formula to obtain the fractal dimension of a fractal is expressed as this n equals s raised to the power d. Remember here, n is the number of small pieces of the fractal, s is the scaling factor, d is the fractal dimension. So the fractal dimension is given by natural logarithm of n upon natural logarithm of s. Now let us see again how does the Sierpiński triangle evolve from a solid filled equilateral triangle. This is the solid filled equilateral triangle. We connected the midpoints of the sides of this equilateral triangle, and we removed the triangle at the center, and the triangle is the open triangle. Topologically, it's an open triangle which we removed here. Okay, so how many pieces are there? Yes, how many pieces are there? What is the value of n? Yes, what is the value of n at iteration 1? I'm asking.
There are 3 solid triangles.
Yes. So the number of triangles, that is the smaller pieces, n is 3. And what is the value of s? The scaling factor, it's half. Is it 2? Is it true?
Yeah.
Or it should be 2.
No, we are halving it, right?
It should be 2. The s should be equal to 2. Oh, it should be equal to 2 because when we scale the smaller triangle, we would be getting the original triangle. Is it clear? Yes. I mean the scaling factor. Is it clear to everyone?
Yeah, it's clear.
So this fractal dimension is natural logarithm of 3 upon natural logarithm of 2. What is its value? Yes, what is its value? Yes. What is the value?
1.5.
1 point. Is it 1.5? Is it?
Yes, sir, 1.58.
Okay, maybe whatever. What I want to show here, this value lies between 1 and 2. It is not an integer. So again, one of the features we discussed about fractal is self-similarity. That is, the smaller parts resemble the whole. That is, the smaller part is an exact replica of the original one. Another feature of a fractal is the dimension need not be an integer, like the square, cube, a line, a point. For those things, we have Euclidean geometry. But when we have an object whose dimension is not an integer, the Euclidean geometry fails there. It is incapable of explaining those objects. So there fractal geometry comes. So this is the fractal which we discussed, the Sierpiński triangle, whose fractal dimension is 1.58, which is not an integer. Okay. Some food for thought for you. Yes, any queries there?
Sir, what does it mean that it doesn't follow Euclidean geometry? I mean, how are the two different?
To some extent, I'm providing the glimpse here that in Euclidean geometry, that is, Euclidean geometry is not able to handle the objects which are very irregular, which are very rough, like clouds, mountains, the Sierpiński triangle, we cannot handle these objects with the help of the theory of Euclidean geometry. If the objects are very irregular, then the theory of fractal geometry comes into play. This is the basic difference. For example, you must be aware of the Weierstrass function. Yeah, what is it? Weierstrass function. What it is? One of you. Yes, what it is? Weierstrass function. It's a very basic function. Yes?
Is it the zeta function?
It's a Weierstrass function. It is a function which is continuous everywhere, but differentiable nowhere. Have you ever seen that function? Yes. See here in the Sierpiński triangle. It is very irregular. If you talk about the differentiability of any piece of the Sierpiński triangle, it fails because at each point it has a corner point. This is the way it is obtained. So such objects cannot be handled by the Euclidean geometry. There comes the fractal geometry. Yes, have you got your answer?
Yes, sir. Thank you.
Okay. So where were we? We discussed the fractal dimension of the Sierpiński triangle. Okay, take it as your homework. Find the fractal dimension of this quark snowflake and the Sierpiński carpet as well, and see their construction as well. How do they evolve? I mean the quark snowflake and the Sierpiński carpet. We have already discussed the construction of the quark snowflake. Go through the construction of the Sierpiński carpet and find their fractal dimensions. Yes, any other query or comments? Yes. Till now, any other query or comments? Yeah. Yes.
Sir, what about the hyperbolic geometry?
Uh,
Are they related? I mean, a hyperbolic geometry is also non-Euclidean in the sense.
In the present scenario, I want to make a distinction between this Euclidean geometry and fractal geometry. We need to discuss it later. We will discuss it later. It has some of the features which are very distinguishing. So we will discuss it later. Hyperbolic geometry.
Okay, sir.
Yes. Anything else? Yes, any other query? Okay. We'll meet in the next session. But please go through all these, the fractal dimension of this quark snowflake, the Sierpiński carpet, and how do they evolve, and go through also some more fractals. Yeah. If you have any other query, you can ask now. Okay, let's wrap up the session now.
Thank you, sir.
Sir, there is a question in the chat box, I think.
Okay. Okay, the last question is, can you tell the use cases of fractals? What does it mean, use cases? What I understand from this question is that you want the answer of where do we use the fractals, is it? Okay. One of the point is that many a time, as I already mentioned, that the objects which are very irregular, we cannot handle those things. Many of the real situations, if we try to have the mathematical model, mathematical modeling of the real life situations, we use the interpolation theory there. But there we have the traditional techniques like Lagrange's interpolation and all those, whatever traditional techniques are there. But the data provided, with that data, the situation, the mathematical modeling provides a regular surface. But that is not a perfect approximation. The approximation, to a better extent, is given by the fractal. That comes into the fractal interpolation theory, one of the applications. Second application, in a healthy body, the fractal dimension, we calculate the fractal dimension of the heart, it is fixed. But what happens if some tumor grows its fractal dimension starts getting changed. So this fractal dimension concept is used in medicine jargon as well to know whether the tumor has grown or not just by calculating the fractal dimension. Yeah, these are basic applications. Any other? Yes. I hope you are convinced with the application. Okay, it seems that there is no further question.
Okay, so anyone have any other query related to fractal? So a bit about the fractal to know is clear. Anything mean to say, if the, yes, Sanant.
Yeah, I mean, is the presentation is done by today?
Yes, yes.
Okay. Anyway, I mean, say it was an interesting presentation, definitely. I mean, from my side, I mean, obviously it's not very technical, but there's a useful tool that I kind of use sometimes to explore fractals. Actually, the name is Xaos, XAOS. Actually, can I share it for a moment?
Yes.
We can at least look at the patterns themselves. Okay, just a minute. Yeah, came across it way later, earlier in fact, and I found that this is interesting to look at. This is the Mandelbrot set actually. This is one of the familiar fractals that we have. But the interesting thing is that we can actually zoom and see the self-similarity over here actually. I can just go in, for example, it can keep on showing us in a greater detail, and we can see the self-similarity over here itself. This exactly the same set that we had seen earlier actually. There are formulas that we can actually see, for example, the Sierpiński triangle or carpet, or in this case, the carpet. We have this particular thing. At least in this case, we might be able to see, for example, how it evolves over there. For example, in this case. So this is I found it very interesting tool. Obviously, it's more, less mathematical. At least, obviously, the construction is mathematical, but as such, not exactly something which I have very, deep. But at least I found very useful because it also gives us, for example, this quant snowflake and how it's actually done. So I think this, I just wanted to share with everybody this particular software.
It's really good. This is XAOS. Yeah, please everyone note it down if you want to know about more fractals. Is really good.
And there's a lot of formulas given as well that you could see over here. For example,
yes,
Newton's formula that we have, cube roots of unity present in the complex plane, and the iterations over there. Anyway, this is the one thing that I wanted to share with you because the theme was exactly that way. That's right.
Yeah, it's really helpful. Thanks, Anand. Thank you so much. So if anybody want to note it that this is XAOS, right?
Yes, XAOS, that was his name.
To get the more idea, picture.
Yeah, even it's good for playing around over there.
Yes. Okay. Anyone have any other query? I hope this session is give bit about the fractal look, how the fractals look like, and how that how mathematically we'll do that. Like what is the meaning of saying to be how the area is decreasing or perimeter is increasing to infinity. Other things of area is it continuously or finite, and the perimeter is again started increasing. If you remove a part from there, how it's happening, that's the fractal thing. Actually, it's the same structure within that you will find as the original one. Okay. So anyone have any kind of query? Himanshu sir is here. Do you want to more? Do you want to know something? You can ask. Otherwise, we'll wrap up the session. And video of this session I will paste in the group, and also in the next when the Pi Square seminar session will happen series, Then I will post the link of now the whatever the 3 sessions we had, and also along with the slides, at least for 2. This one also I will share within the Gmail, and very soon we'll get a YouTube channel. Actually, it is in process. Okay. Okay. Thanks everyone. We'll meet on probably next Friday, or maybe there is a GET exam on or near about on next Friday. Then maybe it's shifted to some other day. We'll notify with the Gmail. Okay. Thanks everyone. Bye bye.
Yeah, thank you.
Someone has raised a hand.
Anyone want to say something?
So someone raised their hand.
Yes, go ahead. Who wants to ask? Yes, I just missed that.
I think Sarthak raised his hand, but now I can't see it. I think no more questions because he put down his answer.
Yeah, please don't forget to fill out this G form. Okay. This is already pinned here. Feedback form. I'm pasting it again here in the chat. You can fill it out. Fill that feedback form and let us know. Okay. And yeah, thanks everyone. Thanks for joining.